Optimization in absolute extrema. In this video, I'm going to go over some problems with optimization in absolute extrema. Now, optimization is essentially word problems involving maximums and minimums. Let's start with this one. Let's find the shortest distance from the point 1, 0, negative 2 to the plane x plus 2y plus z equals 4. Earlier in the course, we saw a way to find the distance from a point to a plane, but we're going to try to find it in a different way. Because the distance from a point to a plane is going to be the shortest distance. Let's start by defining our distance function. And we're going to consider only the points x, y, z that are in the plane. So we're not really going to find the shortest distance, at least not at first. What we're going to do is we're going to find the point that gives us the shortest distance. So the distance from a point x, y, z to a point 1, 0, negative 2 is the square root of x minus 1 squared plus y minus 0 squared plus z plus 2 squared. Now I want to maximize, or in this case, since it's the shortest distance, minimize my equation d. But I'm going to change this slightly because I really want to have a function of x and y only. So I can rewrite this as x minus 1 squared plus y squared. Now let's take a look at the z. Since z is found in my plane equation, I can write z as 4 minus x minus 2y. So I'm going to replace my z with 4 minus x minus 2y. And that's going to give me 6 minus x minus 2y all squared because it's z plus 2. And now let's find some partial derivatives. We'll do the partial with respect to x. This is going to give us 2 times x minus 1 plus 2 times 6 minus x minus 2y, and then times the chain out times negative 1. All over 2 times the square root thing. So I'll just put down 2d. Because I know the denominator is not going to be 0 because the point 1, 0, negative 2 is not in my plane. Meaning I don't really care about the denominator. We'll just set the top equal to 0. And I'm not going to show you all the algebraic steps just for the sake of time. But I will write it out for you. If I do this correctly, we end up with 2x plus 2y minus 7 equals 0. Do the same thing again, but the partial with respect to y. And that's going to give us 2y plus 2 times 6 minus x minus 2y times the chain out, negative 2. All over 2 times the square root, which we call d. That will not be 0. So I can just solve across the top. And if I simplify the top, we end up with 2x plus 5y minus 12 equals 0. So these two things must simultaneously equal 0, which means I can solve these two equations. That is the system. I'm going to rewrite this one and put it down here. So we get 2x plus 2y minus 7 equals 0. Subtracting the bottom from the top, we end up with 3y minus 5 equals 0. Or y equals 5/3. And I'm not going to bore you again with some of the algebra I'm plugging back in. But if I plug in y equals 5/3 into one of these equations, I'm going to end up with x equals 11 over 6. Now, since I have found a critical point, and there is a minimum distance from a point to a plane, and that there's only one critical point, I'm pretty sure that the point I found is going to give me a minimum. Now, if I go ahead and plug this back in, I don't really need the z because I can plug my x and y into that equation up there. We end up with the minimum distance is the square root of 5, 6 squared plus 5, 6 squared plus 5, 6 squared. Now, you might want to stop the video and go through the algebra on your own. But the main point is to show how to set up and solve some of these optimization problems. Let's take a look at another one. Consider a rectangular box without a lid, which is to be made from 12 meters squared of cardboard. Find the dimensions that give the maximum volume of the box. So let me draw a picture. If I'm not sure what to do, I usually start by drawing a picture, at least if it's possible. Sometimes it gives me clues of what to do or how to start, or at least helps me to set up formulas. So I'll call it x, y, z. And I know that the way I wrote this, we have x times y, but there are two of those. When I said two of those, there's only one of those. There's one x times y because there is no top. But I have two x times z's. That would be this side and the back side. And then we have two y times z's. I put a period there for some reason. That is a comma. Let me fix that really quickly for us. And this is going to equal 12 because I found the bottom, xy. That's just a surface area. I have two of the kind of the main sides, like the front and back. And then I have two of these other sides, kind of left and right. And those are all surface areas. And I know I have 12 meters squared total. Now I want to maximize the volume. So the volume is going to be x times y times z. And I really have too many variables, just like the first one. I want to see if I can eliminate the z, or at least solve for z in terms of the others. So from here, I see that z times 2x plus 2y equals 12 minus xy, which means that z is going to equal 12 minus xy all over 2x plus 2y. So my volume equation, which is now going to be a function of xy only, is going to be x times y times 12 minus xy over 2x plus 2y. Or my volume is 12xy minus x squared y squared all over 2x plus 2y. So now we need to find our partial derivatives. So the partial with respect to x is going to be a quotient rule. I like to start by squaring the bottom. I know that x and y can't both be 0 because if x and y are both 0, then my box has no volume and I'm trying to maximize, not minimize it. So I'm not going to really worry about the denominator here. But let's just do the top part, which is going to be 2x plus 2y. Now, times the derivative of the top part with respect to x, which is going to give me 12y minus 2xy squared. And then minus the top times the derivative of the bottom, which will be 2. I'm going to simplify this out a little bit. This will equal y squared times 12 minus x squared minus 2xy all over the denominator, which I'm not really worried about. So again, if you want to do all the algebraic details, I suggest you stop the video and try to work those out. But I'm pushing through, just giving some of the answers just so the video doesn't take forever. Now if I find the partial with respect to y, once again I like to start by squaring the bottom, knowing I won't really worry about it. We'll solve across the top. And we're going to end up with the derivative of the top. So we're going to have 12x minus 2x squared y times the bottom, 2x plus 2y, minus, now we're going to leave the top alone, so 12xy minus x squared y squared times the derivative of the bottom, 2. Set that equal to 0. And once again, simplifying the algebra separately, I get x squared times 12 minus 2xy minus y squared over the denominator, but I'm only worried about the top. So these two must simultaneously be 0, which means these two must be equal to each other because they're both 0. I also know that I cannot have the point 0, 0 as mentioned before. So x and y can't both be 0. So I end up with 12 minus x squared minus 2xy equals 12 minus y squared minus 2xy as well. Getting rid of the stuff that's the same on both sides, we end up with x squared equals y squared, which means x equals y, because I can't have any negative x and y, so I don't worry about the negative x and y because we're dealing with physical quantities. All right, so since x must equal y, I can plug it back into an equation like this one. I can plug that fact and say 12 minus 2x times x minus x squared equals 0, giving us 12 equals 3x squared, which gives us x equals 2. Can't be negative 2 once again, but I know x equals y, so y equals 2. And then I could plug x and y back into my z. So z at 2, 2 is going to end up being 8 over 8, or 1. So the dimensions that maximize the box are 2 meters by 2 meters by 1 meter. All right, let's look at one absolute max and min problem. This is going to be a bit of a long one. Let's start with the extreme value theorem. So if f is continuous on a closed bounded set, a closed bounded set would be something like this in the xy plane, all the points in between. Not bounded would be something like this, where we don't include the endpoints. So if f is continuous on a closed bounded set, then f will contain an absolute max and min value on this domain D. This is just like single variable calculus. The corollary, the extreme values will occur at a critical point or on a boundary point. In single variable, it was an extreme value will occur at a critical point or an endpoint, where the endpoint was a boundary point. So it's a very similar idea, but there's a lot more work to do. Let's do one example where we want to find the absolute max and min values of f of xy equals x squared minus 2xy plus 2y on the domain all x's and y's such that x is between 0 and 3, y is between 0 and 2. I'm going to draw a picture of that. I want to see my domain. So x is, say, 1, 2, 3, y is 1, 2. So what we have here is a rectangle, including the boundary points as well as the interior points. So this is my domain, and imagine my function is coming out of the screen. Find the absolute max and min values of this function somewhere on this interval. All right, let's start by finding critical points. So f of x is 2x minus 2y, and that has to equal 0, which means x must equal y. F of y gives us negative 2x plus 2 equals 0, which gives us x equals 1. But since x equals y, the critical point is the point 1, 1. Now, just like in single variable, we can check endpoints and boundary points and plug these into our original function without doing other work like finding the second derivative test, and just get values and see which are the biggest and which are the smallest. So if I plug in the point 1, 1, we get 1 squared minus 2 plus 2, which equals 1. All right, now here's the part that's going to take a little while. How do we find the values on the boundaries? So we're going to do one boundary at a time. I'll call this boundary A, and then we're going to go clockwise B, C, and D, and look at each of these boundaries individually. So let's look at A. Notice that A has the points x equals 0 and y equals something between 0 and 2. All right, so on A, x always equals 0, and we have some y between 0 and 2. So I'm going to look at the function values at the point 0, y. So we're going to go back up to the top and plug in 0y into my function here, which is going to give us f of 0y equals 2y. Right, we get 0 squared minus 2 times 0 plus 2 times y, or 2y. So right above this segment, this line segment, my function is simply z equals 2y. Now notice this function is increasing on 0 to 2. So we can find f of 0, 0. And f of 0, 0 is 0. And we can use our simplified version to do these. And then we can find f of 0, 2, which is going to be 4. Why do I not need to check points in between? Well, it's because the function is increasing on an interval. So it's going to be the smallest at the starting point and the largest at the other point. All right, now let's find part B. And at part B, we don't know what x is, but we know that y always equals 2, and this is for x between 0 and 3. So let's find f of x comma 2 on the interval 0 to 3. So if I plug in x for x and then 2 for y, we end up with x squared minus 4x plus 4, which equals x minus 2 squared. So above this top line, z equals x minus 2 squared. And if we think about this just a little bit, we know that on that line, f is going to decrease from 0 to 2 and increase from 2 to 3. Just think about my parabola. It would look like that. So when x equals 0 and y equals 2, well, we already know what happens there. So we have f of 0, 2 is 4. I'll rewrite it. We found it in part A. We also need to check what happens when x equals 2 and y equals 2. So f of 2, 2, if I were to plug it back into my function, is going to give me 0. And then f is increasing again, so I need to check the far endpoint. So x is 3 and y is still 2. And when I plug that in, we get the point, or the value 1. All right, we got to do this just a couple more times. So I'm going to rewrite my function down here so we can see it, so we don't have to keep scrolling back. So f of xy equals x squared minus 2xy plus 2y. All right, I guess I'll have to scroll back a little to see my picture. So now we're going to look on this right side. And notice on the right side that x is fixed again and y is changing. And it doesn't really matter if I go up or down. I'll just know that y is between 0 and 2. So f of 3y, that's 3 comma y, plugging it back into my original function, we end up with 9 minus 4y. And this function is decreasing on the interval 0 to 2. That is 0 less than y less than 2. Now I already know f of 3, 1 equals 1. And then I can find f of 3, 0, which is 9. Again, the reason I'm finding decreasing or increasing is to show that I don't need to check points in between some of these endpoints. Because if a function is strictly decreasing as y goes from 0 to 2, I don't need to worry about y equals 1 or 1.5 or anything. because the value will keep decreasing as I go forward. All right, the final one. The final side D, and again, it doesn't matter which way I go, but notice that x is changing, but y is always 0. And we're on the interval 0 to 3 for x. So f of x comma 0 is x squared. So y equals x squared. If I draw that, I'm on 0 to 3. I'm strictly increasing, so I don't need to worry about any intermediate points here to here. I only need to check when x equals 0 and x equals 3. So I need to find f of 0, 0, which I already know. We did that already. And I need to find f of 3, 0, which I already know is 9. So now let's put this all together. What is the absolute max and absolute min value? Well, I can choose from 1, the value at the critical point, or 0, so 1 is not the min, or 4, so 1 is not the max, so I don't need to worry about that anymore. I have 4 again, don't need to worry about it. 0 again, 1 again. Then I have 9, and 0 again, 1 again. So I found that the absolute max value equals 9. And that occurs at the point 3, 0. And then the absolute min value equals 0. And this occurs at both the point 0, 0 and the point 2, comma 2.